Welcome to another session with my little TangerineTiger. It's been a couple of weeks now since I've really played with this machine because I've had other things to deal with. But hey, we're getting back on the case now. Last time, if you remember, we managed to establish that the expanding beam could be controlled with a beam expander. And I made my own little crude holder to put the 3x beam expander in front of the RF laser. It was adequate to prove the point that the beam expander worked, and that we went from a 2mm beam to about a 6mm beam, whether we looked at it about 100mm away, or in fact I checked it about 3 meters away as well. It looked to be doing a pretty good job of making the beam pretty parallel. So I then inquired of CloudRay if there was such a thing as a piece of standard kit that would allow me to fix that onto the front of this "you can buy it everywhere" type RF laser. There must be some adapter plate that allows me to connect one of these beam expanders straight onto the front there. There didn't appear to be, so I designed something and sent it to CloudRay and asked them if they'd make a prototype. The good news is they didn't. What they found instead was a standard plate of some sort from somewhere. Now I don't know where they found it from, but they've sent me A standard plate, B a 2x magnifier, so we can test the 2 and the 3 to see what effect they have. Now here is the plate that they sent me. As you can see, it fits perfectly. It only locates on these 4 holes at the edge here, but they're pretty accurately machined holes, and when I check in there it looks as though it's pretty concentric. Now the great news is all I have to do is to screw this in and job is done. But I'm not going to do that to start with. Now although I'm anxious to get on and use this machine, I don't think I really ought to rush it, because I really ought to understand how this thing works before I start trying to make it do something. I want to go about this journey of discovery in a much more logical fashion than I did when I knew very little and was floundering around in the dark with my China Blue machine. My first task will be to measure the power that is coming out of this device. It says it's 30 watts. I think that that's 30 watts CW, continuous wave mode. Now, I've got no idea how this machine is programmed at the moment and what's going to come out of here. But because this is a pulsing system controlled by the PWM, so it could well be that the pulse is 30 watts, but the pulses are regularly spaced out, for example, such that we've got 50% on and 50% off. Now what that means is, although we've got 30 watts per pulse, we shall only have an average power of 15 watts. So what I measure on here is a little bit of an unknown at the moment. That doesn't make any difference, because what we want to find out is the relative change of power as I move further away from the beam. Technically, you wouldn't expect the laser beam to lose its power with distance. I know it changes its diameter with distance, but the power should still be there in the beam. I want to prove that before we start, because I want to get to 1.3 meters, which is about where you are at the moment, because I don't want to lose power as I go around this very small machine. Now I've already got my little doohickey test program set up on the machine that runs for 20.5 seconds. Well, I'm going to check first of all what's happening straight out of the tube here. Now I've got something in the region of about maybe 5 or 6 seconds before the beam will start coming out of here. One other thing that I've noticed, and I'll have to explore further, this is completely cold at this moment in time. I have read somewhere that it takes maybe 10 minutes for this to warm up to its proper output value. Seems a bit strange, but hey, that's what one of the specifications I read said. For the moment, we're going to check it from cold, dead cold, because this has been sitting here for, well, as I said, a couple of weeks now. 18.2 to 38. So we started off at 18.2, we finished up at 38. The difference in temperature, the temperature rise is 19.8, and we're using the ×2 scale, which means if I multiply 19.8 by 2 I get 39.6. This is a 30-watt machine. So, hey, we're doing something pretty remarkably good here. Well, this time we're starting off at about 18.6. Now, from all the work that I've done previously, I would expect to lose something in the region of about 4% per lens, just as a guide. So dividing that by that gives me 95%. So that means I've lost 5% over 2 lenses, which is not bad. That's the times 3 device. Let's try the times 2 device and see what that gives us. Here's the times 2. Look, I'm just about to tighten this up onto its shoulder. If I loosen it off just a little bit, look, I could physically move this maybe 1/2 to 3/4 of a millimetres either way. So that's a pretty dodgy old thread in there. That looks like a much bigger loss. 36.6, 37.8. That's another watt that's been lost because we've done times 2. Do I believe that? No. Because it's possible, remember what I said to start with, this thing has got a warm-up period, that things might have changed in the 5 or 10 minutes that this has been running. So the check that I shall now make is take the beam combiner off and check the wattage again. Do I get the same value as that one? 2 times is about what I expected, 4% loss per lens. Okay, so I've got a piece of card there set up 1.3 metres away from the front of the tube, and I've got no beam combiner on it at all. I'm going to fire 100% power at it just quickly to find out where I am. And there is the answer. Now we do a bit of a real target test, because first of all I've stuck a piece of acrylic onto the card so that there's somewhere for the energy to get absorbed if it burns through the card, and I don't want to set fire to my cardboard. But I'm also using a card there which is in front, which has got quite a high kaolin content. In other words, it won't catch fire, I hope. So I'm hoping to be able to get a decent scorch mark which tells me the real size of the beam when I can hold it on for long enough. And there we go. I think that's probably about as big as the beam is going to get. I would say that that's close on 10 millimetres. We know we're starting off with approximately a 2mm beam. I'm going to put the times 3 beam combiner on, and I'm going to move the laser very slightly to the right. We'll measure it properly later on, but it's somewhere between 7 and 8, so it's not too far off it. I have to say that is substantially better, but I would probably put that at about 6 millimetres. We'll just check that we're still in the right place. Yes. I'm quite pleased with that, because, okay, we are getting a power loss, but I was only expecting 30 watts to start with. We happen to have 38 watts average power, okay, which is a lot more than I was expecting to see, and we've only got 1.4 watts loss. Right, let's turn that noise off. I'm going to have to deal with that in some way later, but let's just live with it for the moment. So yeah, 6 millimetres, 10 millimetres, and 7.5 millimetres. Now 6 is a very nice number, because that's the sort of number that I would expect to see out of a glass tube laser. So we're definitely going to go with the times 2. Now, I just spotted something rather strange and interesting, which we shall have to go back and check. That there was with the beam combiner on. This here is with the beam combiner on. That doesn't make sense. We can't have gained because we've gone further away. I was expecting a loss further away, so I've actually taken the wrong two numbers here. Okay, so this stability and warm-up thing seems to have some truth in it, because when I rerun the numbers, I'm getting 37.6 watts. When I move away 1.3 meters with the beam combiner on, I'm getting 38 watts. So I'm still getting more watts close up than I am when I'm 1.3 meters away. Now that sounds like a miracle, but in fact I think it's probably just the system is not capable of resolving to these 0.1 of a watt or something like that. So we're losing 7% because of the beam combiner and nothing because of distance, which is brilliant news. For some reason or other, we seem to have a 40 watt unit almost. I don't know, but it turns out that this unit might be 40 watts. There is no external difference between a 30 watt and a 40 watt unit. And the paperwork definitely said this was a 30 watt unit, but I've got half an idea that that was Cloud Ray devaluing the unit for customs purposes, because the 40 watt is about $400 more. So yeah, they've saved quite a lot on duty by doing that. But anyway, we're going to put this back together now that we've checked everything out. I'm going to assemble the mirror and then we'll go through the setup procedure. I'll set the beam up. I'm going to go and set up my Y-axis now. I've got the beam approximately through the hole. Now, I already had this machine set up in the Y-axis once, so it shouldn't be too far out. But normally this would be several stages to get this right, but I don't know how many this is going to take me. Let's just have a go. See what the second one is like. It's not bad, it's a little bit to the left, isn't it? Probably just a shade too far. So because it's so close, we should have to do it again. You can always use the back of the targets, because we're not trying to get it on centre, we're just trying to get two dots that coincide. So let's just make a target and we'll see how close we can get with this one. Spot on. So that was a couple of goes with getting Y, but hey, this is a bit abnormal because I wouldn't normally have the machine set this well. I've designed some special targets for the Mark II head because there are one or two oddities about the head that we need to take into account. So the first thing that I've done is manufactured a target like this. But these fixing screws appear to be too long. Well, they're not too long, they're designed so that you can plug a target onto them, like that. And then at the other end of the stroke, where we've got a little bit more light, not bad, just a little tweak to the right. Now this is where you just can't get your fingers in there to adjust these screws, and this is where you now need the access panel that's on the side here. It's now just about spot on. It just so happened it was in the centre of the target, but that does not mean to say that it's in the right place. So we can use the back of that target on the table. We can fire a spot down onto that target. Then we can drop the table down. This is very, very, very slow, this machine. There we go, 3 or 4 inches. Now we'll check again. And we're out. Pretty good, but hey, we've got to do all that again now. As I've warned you previously, although we've got this thing set up mechanically square, you need to just check to make absolutely sure that it is sitting upright and square. So this is set upright in both axes, and now we do it again. There we go. Now that's a nice round spot, I have to say, and it's also nice and small. So remember, we've had one attempt it probably is going to take 3 attempts to get this set. So it's a very laborious process when you've got a slow table like this. Right, second pulse is out. So we need to bring it across. More. A little bit more. A bit more. Pretty well there. Now we've got to come forward a shade. Just a shade more. Too much. That's pretty good. We've got another target here, which is square, and it's got a little tab where you tear it off. That tab needs to be to this outside edge, but there's a hole in there, which makes sure you put that hole in that corner. And that's the centre that we're looking for when we bounce off this mirror. So let's see how good we are for the centre of the lens now. Not bad actually. So we're pretty good that way. So we haven't got to raise or lower the mirror. What we've got to do is just bring it slightly this way with the y-axis adjustment, which is over on mirror number 2. So we'll just loosen mirror 2 off. And it's got to come across what? Maybe 3mm? A quick pulse. Too much. See if I can leave it loose. There we go, just about spot on. And that's how easy it is to set up wide. We'll just check it now that I've tightened it back up. There we go. So our beam is now passing right down the central axis of the lens, and we're going to get an upright cut. As a final check I like to perform, you've got to look at it at just the right angle because the light is wrong. It's not far off the centre, as you can see. I'm pretty pleased with that for a setup. Now I said I wasn't going to play with this machine until I've got it and understood it a bit more, but I'm so fascinated by the size of that dot that I'm actually going to run a very quick dot test on here at 400mm a second and 25% power, just to see what we've got. Origin, and off we go. I obviously haven't set the accelerations up yet. I would say that they're probably about 0.15 dots that I can see on there. They're not 0.1 dots, but they're certainly all separated, which for a 2-inch lens is pretty good going, and that bodes quite well. Now I don't want you to laugh, but in an attempt to quieten this thing down, I have modified the back panel so that it allows air in, and I've put an upward deflector on it to catch the sound. Maybe it'll deflect the sound downwards. Let's see how this works. Right, does this make it any quieter? A little bit. Take some of the high frequency away, and certainly from the front of the machine here it doesn't sound too bad at all. I could live with this. I think the extraction is now going to be louder than the RF unit. We don't need that noise, do we? It's still annoying, isn't it? But hey, I'll leave it like that for a little while. Oh, by the way, don't worry, there is plenty of air coming out the end here. I've taken the end panel off, so all my air is exhausting out this end. Well, this has actually been quite a successful session. We've managed to establish that we've got a good beam, we've got no loss of power, and we've set the machine up pretty accurately. We've seen the potential for getting very small dots at high speed. And we haven't even tried to set the machine to do it at the moment. It's doing it on its own. So, lots of promise, but we've got lots of laborious things to explore and check out before we really get into the depths of this machine. How does the RF tube actually actually work. I'm about 80% of the way to understanding how that works. And it's been a difficult process because there's not much out there telling me how it works. Thank you very much for your time again, and I'll catch up with you in the next session.